I got a pretty important phone call recently. President Obama called me up. I was pretty surprised. I was brushing my teeth, whatever. He calls me up and he's like, "I've received grave news of a grave threat. Unless you re-implement Ruby's hash, alien terrorists will blow up SeaWorld." Blow up SeaWorld. That guy's Obama impersonation is terrible. Sorry. So I said, Mr. President, I love aquatic mammals as much as you do, but that really makes no sense. I thought it was going to, hang up and blow it off, but I looked outside and I saw this van, and I thought maybe I should at least give it a shot. So everybody knows what a hash is. A hash is a data structure. We use these all the time. Basically, it's a place to put values that you associate with keys, and you can ask for that key and get that value back. Some languages call this a map or a dictionary. And our goal is basically going to be, let's implement this. Let's make our own hash class that works just like that. Piece of cake, right? We can totally do this. Here's the implementation I have in mind. Okay? Inside the guts of this thing, we have an array of arrays. We've got a bunch of little arrays. Each of them is a pair of keys and values. So if you say, I would like to see the value for cat, I can just walk through these little arrays of arrays until I find one that the key is cat, and I can give you back gato. And if you try to insert a value, simple, I can just go along until I find the correct key, update the value. If there isn't one, I'll insert a new tuple. Piece of cake, right? That's going to work perfectly. So I also know that Ruby has all kinds of lovely syntactic sugar. You can define your own equal methods and stuff. So to get the nice little bracket notation, I'm going to define this reader and this writer, and then it'll look just like it's supposed to. Now you notice I'm calling this class tuple map. It's not really a hash, but it's close enough. And it uses tuples, so that's a good name. So I built this class, I tested it, everything looks well, it works just like this. Hokey is pokey, and you can get it back out. Thumbs up. Wrote an email to the president, attached my class, and said, there you go, sir. Called it a day. Well, I got another phone call. He said, let me be clear, that's not good enough. He said, now my eggheads tell me that your hash is O of 1 and it needs to be, your hash is O of n and it needs to be O of 1. I don't know what that means, but I want you to fix it. I said, you're changing the requirements on me? Is that what happened to healthcare.gov? I can't live under this kind of pressure. The problem is, his eggheads were right. O of n and O of 1 are very different things, and we do have an O of 1 hash, and that's not good enough. But what the heck does that mean? Now, probably a lot of you have computer science backgrounds, but I don't, so I'm going to talk to the ones of you who don't, and this is going to be computer science by noobs for noobs. I'm going to explain the concept of big O and why this is so important. When we talk about big O notation, the O is for order, like order of growth, and we're really talking about rates of growth. Let me give you some really simple illustrations. So if I were going to do a task like go around and shake hands with every one of you, that's O of n. If there's 10 of you, I've got 10 handshakes to make. If there's 100, I've got 100 handshakes to make. Very simple, right? It scales like that. What if I were going to try to introduce every person in this room to every other person in this room? That's O of n squared, right? If there's 10 of you, there's roughly 100 introductions to make. I'm fudging a little bit. If there's 100, there's roughly 10,000 introductions to make. That scales really poorly. But something that scales awesomely is waving at you, because I don't care how many of you there are. This is O of 1, right? And the great thing is that the n describes the number of inputs. So in this case, the number of inputs is how many people are we dealing with. And you notice that in the phrase O of 1, the letter n does not appear, because it's completely irrelevant. So when we're talking about an O of 1 algorithm, that's great. That means it doesn't depend on how many inputs we have at all. Orders of growth are a way of describing how does this algorithm scale. As we throw more and more work at it, does it scale well or does it scale poorly? So if you have an algorithm to sort a list, and I give you a list that's twice as large, does it take you twice as long to sort it, or less than twice as long, or more than twice as long? How does that scale? Now, the thing that we really care about when we look at a diagram like this is how is it shaped? You notice that these things are all shaped very differently. These are all different orders of growth. We have, for example, a linear growth here on the yellow line. We have some exponential growth. We have some logarithmic growth. And what makes each of these different is their shape. We can get involved in talking about how algorithms perform in absolute terms. But when you graph these things, the angle and the location are things that we ignore when we're talking about big O. So here's an example of O of 1. All of these lines are O of 1. Now, in absolute terms, if you have an algorithm that performs like any of these, these differences may actually matter to you. So on the x-axis, we have the number of inputs to this algorithm. On the y-axis, we have how much work does the algorithm have to do. If you're dealing with the blue line, that's obviously much better than the red line. Your thing takes 5 steps instead of 9 or something like that. And you might want to optimize to try to do fewer steps to do less work. But in terms of growth, these are perfect because how they grow is they don't. You throw more and more work at it, and it just pretends like nothing happens. It just continues to perform exactly as it has. Linear growth is something that basically is a straight line with slope. Now, in absolute terms, again, these different curves, you would care about the differences between them. So the red one, you have maybe 1 unit of work to do per unit of input. The steeper line, you have maybe 5 units of work or 10 units of work to do per input. If you could manage to optimize that so you can do 8 steps instead of 10 steps or 2 steps or whatever, that would be great. But in big O terms, those differences are irrelevant because these are straight lines with slope. Again, we've got a line that doesn't even intersect with 0, 0. That means even if you have no one input or like at the minimum possible inputs, you have some amount of work to do. Maybe you have to boot the JVM to get started with whatever you're doing. But again, in big O terms, that's irrelevant. That's position. We don't care about position, and we don't care about angle. We only care about shape. Now, why does this stuff matter? This stuff matters because if you think about how these graphs are going to extend out, these differences are only going to multiply and become larger and larger. So a famous algorithm that people talk about when they're talking about orders of growth is the Traveling Salesman problem. You've probably heard of the Traveling Salesman problem. It's basically, you've got a person who wants to visit a bunch of cities, and they want to visit each city once, and they want to come back home. And you want to find the shortest path to do that. So the brute force approach is you try every possible route, and then you figure out how long each one of them takes, and then you rank them, and you return the top result. That approach, that brute force approach, is big O of n factorial, which means if there's 10 cities, you have 10 times 9 times 8 times 7, all the way down to 1 steps to do. If it's 100 cities, you have 100 times 99, all the way down to 1 steps to do. So it grows very quickly. It's very difficult for us as human beings to have in our minds what that kind of quick growth actually looks like. So suppose you have you're doing this brute force approach, and 5 cities takes you 0.12 seconds. Does anybody want to make a guess, and I'm going to make you look foolish probably, how long it would take you to do 21 cities? 5 cities is 0.12 seconds. How long is 21 cities? Anybody? It's crazy. 97 billion years. It's crazy. So it's really important to know if your algorithm is scaling n factorial, because think about this. Maybe you work for a travel search site. I happen to. Somebody says, hey, we got this great idea for a feature. We're going to help people plan their trips. Okay, you can offer that feature for 3 cities. You can offer that feature for 5 cities, but don't try to offer it for 10, because the person will have taken the trip and come home before you finish. And don't try to offer it for 21 cities, because your server farm will melt, and you will be out of business, and the sun will burn out, and you still won't be finished. It's important to know what big O category your algorithm falls into. And the big idea here is, in the long run, it doesn't matter how high it is, any O of 1 algorithm is going to beat the pants off of any O of n algorithm. And any O of n algorithm is going to beat the pants off of any O of n squared algorithm. So if you can optimize a little bit within the linear category, that's good. But if you can change categories from O of n to O of 1, that's a huge, huge win. So what is our big O problem here? Why is this big O of n? Well, if you think about it, it makes sense, right? You say to me, I want the key cat. Well, I have to go walking through every one of these inputs until I find one where the key is cat. Obviously, if there's 1,000 of those, it's going to take me a lot longer than if there's only 3. So we're scaling up. This is going to take us longer depending on how many inputs we have. This isn't good. One of the great features of hashes is that they're O of 1. It should be the case that no matter how many keys you have in there, it takes you the same amount of time to look something up. Now, this is a measurement. I actually have built this tuple map class, and I've done some measurements to show that, in fact, it does grow linearly. So here what I've done. On the x-axis, you have larger and larger sizes of hashes. So you've got anywhere from 150 to somewhere like 14,500 keys in the hash. And the way I've done this test is really simple. Basically, I do a measurement round, I do 150 inserts, and then I do 150 reads. And then I do another round. And you can see it just grows like that. So it does grow linearly. This confirms basically what we've figured out by looking at the code. So the question is, how can we implement the internals of this thing in a way that's O of 1? What do we know that's O of 1 that we can use? Well, one thing that we know that's O of 1 is array lookup by index. So if I have an index like this and I say, I want item 328, or if I say I want item 5, it's going to take the same amount of time to look them up. It's going to be just like that. Okay, but how the heck does that work? Well, because RAM. This is where we get a little hand wavy about the details, but RAM is random access memory. And what that means is you can access any random place in the memory just as fast as you can access any other random place in the memory. That's completely unlike a spinning disk, right? And a spinning disk, if the data's over here and I'm over there, it's going to take me a while to get to it. RAM has this lovely feature. And because it has this can work really nicely. Because all we need to know is, where is the thing in RAM that I'm looking for? If I have the address, I can ask RAM for it, and it'll give it back to me instantly. Well, in the same amount of time. It doesn't matter how long it takes. What matters is that it always takes the same amount of time. So the way that this can work is in Ruby. Ruby knows where the beginning of your array is, and it knows how wide each slot is, because each slot is the width of one pointer in memory. So it can say, hey, you're trying to go 5 slots in. I can multiply 5 times the number of pointers. I can multiply the pointer size times 5, and that's how far it is from the beginning of the array. I can figure out the address in RAM, and I can go right there. So that's why access by index is going to work really nicely for us. So let's make a new plan. How can we make the guts of our hash depend on this? It's going to have basically 2 parts. We have a sparse array, which is like this. We have a bunch of blanks in it, and then wherever we want to put some data, we have data there. And then we have a digest function to help us figure out where to put data. So the digest function is a way of taking some key that you want to store and turning it into a number, because we need to know the position in our sparse array to store the value. So you can think of a digest function. Sometimes these are called hash functions, and that can be confusing because we have hashes and we have hash functions. And Ruby, very wisely, generally calls this library digest, which I think is a great name because it conveys what it does. Because just like digestion, digest functions are one way. You can't take poo and turn it back into pizza, right? Or at least not the same pizza. So we have a one-way function that's going to turn our string into a number. And we need a number because we need to know an array position. And if we can do this, then we'll know exactly where to put it, and somebody will come back and say, hey, I want the appetizer key. And we'll say, oh, great, I can turn that into 2. I can go straight to this position 2 in my array. Here you go. There's your value. That's going to work beautifully, right? Yay! Problem solved. Well, not quite. We have some problems. Our first problem is collisions. When we do our hash function, we have no way of guaranteeing that every key is going to produce a unique value. In fact, it probably won't. So we hash the appetizer, we do a digest of the appetizer key, and we do a digest of the mammal key, and oh no, they both come out to 2. Well, what do we put in slot number 2? Our solution is to have buckets. So at slot number 2, we don't have a thing, we have kind of our old familiar key-value pairs like we talked about before, which is nice because now we can put both things there, and we can figure out when we go to look for appetizer what is the actual correct value for it. But you can see that that's going to sort of reintroduce the same problem, right? If we get to that bucket and we have to walk through all the things, not so good. We'll come back to that. Our second problem is waste. Sure, it's great that we have this value in slot 2 here, but we've got all these other nils. We're going to have a lot of nils just sitting around in memory doing us no good. So what a waste of memory, right? We don't like that. We want to be efficient. Our solution is get over it. Mostly. This is a crucial thing to see, though. Hashes, as they're really implemented in Ruby, as they really work, are a trade-off. We're trading off memory for speed. We're saying we're willing to waste a bunch of memory on that sparse array so that we can get to the thing we want really quickly. So is there a grand solution that we can come up with which minimizes collisions? Because the more collisions we have, the more full that bucket is, the more things we have to look through, the worse the performance is. We want to minimize collisions. We also want to minimize wasted memory. Is there a grand solution for that? Yes, our solution is going to be this. We're going to grow as needed. We're going to say, we're going to trade off some RAM so we can continue to have good lookup speed, but not a lot. And as we need to, we'll trade off more. What does it mean to grow as needed? Well, you could define this in a lot of different ways, but I've chosen a really simple definition. When any bucket has 10 keys in it, time to grow. You do an insert, I find that I'm putting it in a bucket that's already pretty full, 10 keys, time to grow. Well, what does it mean to grow? This is crucial. It's important that when we create our new sparse array, we spread things out. So on the left, we have the old situation where we have things piled up a lot. That last bucket only has one item in it, but every bucket has something, and most of the buckets have more than one thing. When we grow, we want things to be spread out so that we have a bunch of spaces again, and then we don't have many things that have more than one in it, because otherwise we've just got the same old performance problem. And another thing to see is that when we grow, the way we do that is we have to go back through every key and rehash it and put it into the new, larger, sparse array. It's going to be a matter of going through every single key. So here's our basic strategy. We're going to start with X number of buckets. We're going to compute whatever key you give me. I'm going to compute the raw digest value. Somehow I'm going to get a number. Let's skip over that for right now. And then we're going to take whatever that number is, and we're going to do it modulus the number of buckets, and that'll tell us which bucket to put it in. You probably all know what modulo is, but I'm just going to make sure you're all with me, because I want you to be able to make a hash when you're done. So modulo is just a way of saying, divide by this number and take the remainder. The nice thing about it is, as you can see, I can throw any of these numbers on the left at it, and I always get one of three values. So if I do this, then any numeric value that I get, I know it's going to end up giving me a valid array slot in my sparse array if I have 3 slots. Now, the other thing that I want is not only to pick a sparse array size that I can use, but also to be able to make it so that when I grow, things spread out again. So if I were to grow from 3 to 7, you can see as I do modulo on all these numbers, 3 versus 7, most of them don't come out the same. And that's good, because I don't want everything to show up in the same slots again. I want them to show up in different slots, mostly. So from 3 to 7 would be a good way to grow. But how can I generalize that? I want to be able to always know, hey, if I'm at size blah and I need to grow, what do I grow to? What's my new size? Well, the growth strategy that I picked, and I'm not going into too much detail on this, but is to double the size and find the next prime. It's important to double the size because we want to make sure that we don't have to do this too often, essentially. And it's important for the number to be prime so that we don't rehash things to the same slots. I skipped over this. How do we get a raw digest value from a key? Now, I initially started by rolling my own, but let me just give you an idea of what the requirements are for this method. It has to be able to convert any object to a number. My first attempt was something that depended on strings. I said, I'll take this string and I'll convert it to Unicode code points, which are numbers, and then I'll smash them all together, and hey, look, I got a number. Well, but you have to be able to use arrays as keys in Ruby, and really any object. Any object can be a key in Ruby. All right, well, all objects have an object ID, right? So I could use an object ID, but that's not going to work because I want to be able to set something with the string A, and there's a different string, A, and I want to be able to get it out. I don't want to have to save a reference to the key I used and use it again to get it back out. That's silly. I need to be able to have same value keys, quote unquote, be interchangeable. But what does that mean? I mean, I don't know what same value means for you. Same value is kind of a fuzzy concept, right? So I've got 2 people out of the people collection, and I put something into the hash with one of them, and can I get it out with the other one? Heck if I know. How do I know if 2 people are equal? So the solution that Ruby uses is to ask the object. It's the object's job to tell you what objects it's equal to. So every object in Ruby has a hash method, and that hash method produces a number. And these are just some examples. And the contract that the hash method holds up is that hash and equal must agree. So these two arrays are not the same object, they don't have the same object ID, but they are equal in value, quote unquote, according to them. And they also produce the same hash value. So they uphold this contract. Now, if you want to have some custom class of yours, like person, and you want to use those as array keys, and you've decided for whatever reason that two people are equal if they have the same first and last name, that's fine. You can do that. But if you want to use them as hash keys, and you want it to work properly, you have to define the hash method so that any two people that have the same first and last name will produce the same hash value. This took me a while to figure out. Okay, so here's a review of what we've figured out so far. We have to take the key and turn it into a number using the hash method. We're going to do modulo the number of available buckets, and that'll tell us the index of the bucket we want to use. We found out that growing produces fewer collisions, and that helps us to be fast. That helps us to maintain the speed that we have. We've also found that growing means we use more memory. As we grow our hash as needed, we're eating more memory. We're making that trade-off. But in the course of this implementation, our whole goal was to get O of 1 performance. So if I were to graph, like a graph tuple map, if I were to graph my new class hash map and say, okay, for lots of inserts, for lots of reads, I should see not a line that's increasing linearly, but I should see a nice flat line, right? You should be able to say, if I have a hash with 1,000,000 keys in it, or if I have a hash with 10 keys in it, I can read from it at the same speed, I can write to it at the same speed. So did we get O of 1? Are you guys psyched to see the graph? Can you please give me a hand for the graph? Woo! Yeah! Oh. Well. So this kind of looks good, parts of it. So let me explain what we're looking at here again. On the bottom, on the x-axis, we have size of the hash, right? So we have anywhere from 100,000 entries to 9.7 million entries. I imagine most of your hashes don't have that many. And the bottom line is the number of reads. So for 100,000 reads, how long did it take? And the upper line is for writes. And you can see that no matter how big the hash is, it takes about the same amount of time to do some reads. So that's nice. And then you can see on the line with the writes, basically it stays flat, right? I mean, over here, we can do a bunch of writes just as fast as we did when we were really small. We just have a few little issues there in the middle. Kind of some spikiness. Okay, well, let's think about what those spikes are. Those spikes are when we redistribute, right? Because every time we grow, we said we have to go back through all of the keys that we have. We have to rehash them to figure out where do they land in the new slot, in the new sparse array. Okay, so we expect to have some spikes. What if we look at the native Ruby hash? Does it have this kind of signature in its performance? Well, in fact, it does. You can see that it stays pretty linearly as it grows, but it also has some spikes. And I expect that it's doing exactly what we're doing. It's redistributing as necessary. Okay, well, how big were those spikes? They went off the screen. Oh! 48 seconds. Ouch. Folks, you don't want to use my hash in production. I mean, I doubt that you actually have hashes this big, but still, the native Ruby hash is much nicer. But look, before we feel like we're failing at this task, take a look at what we've got. They both have pretty linear performance between the spikes, and pretty much O of 1, pretty flat performance between the spikes. And the spikes themselves follow a linear pattern, because every time you get to a point where you need to rehash, you have more keys to deal with. So, in big O terms, this is the same, right? We don't care about slope. Sure, mine is sloped like this, and the native Ruby hash is sloped like this, but they're both linear. So, hey, thumbs up. And if we zoom in again, like I said, all of the parts in between the spikes are flat. So what about those spikes? Can we call this O of 1 performance, or can't we? Well, I'm going to say it's success, and here's why. Because reads are always less than 10 steps. We never allow more than 10 keys in a bucket. So thumbs up, that's O of 1. You might say, oh, that's O of 10. No, it's not. That's a slope thing. That's a position thing. We only care about shape. We call that O of 1. Well, writes are also O of 1. They're also the same number of steps each time. You got to do the hash, you got to go to the position, you got to write. The end. Except for if you happen to be unfortunate enough to do a write at a point when it realizes it needs to grow. Okay, well, what about that growth? Well, the growth does take n steps. But the interesting thing is, as it gets slower, it also gets less frequent, because we double each time. So if you think about these things as little mountains that are like each mountain is taller than the last mountain, it's also got a larger valley in between it and the previous mountain. So if we take and squish those down into their valleys, they end up the same. So essentially, the number of steps we have to do per insert, on average, stays the same. This is called amortized analysis. We're saying, essentially, like all the writes you're doing leading up to that spike, you're kind of incurring some debt, because eventually you're going to have to rehash. And then some unlucky write causes it to actually do the rehashing, and that pays off the debt. But if you look at it in amortized terms, if you spread it back out, it actually ends up being on average the same, and we call that O of 1. Woo! Yay! So I attached this to an email, and I sent it off to the president, and I was feeling very fine. So, as I said, you wouldn't want to use this hash that I just built in production. It doesn't have the years and years of optimization that the native Ruby hash has. It doesn't have the lovely code written in C so that the slope ends up being really low. And we could figure out ways to optimize this, right? We could trade off more memory at a time so that the spikes come less often. We could maybe rehash in a background thread or something crazy. So say somebody does an insert, we say we don't want to make them wait around on this, so we'll just take the value and do our rehashing elsewhere. We could implement this in C so that it actually runs faster. But again, remember, that's about optimizing slope, not about optimizing shape. And there are some applications of this. You might think, well, this is really nice, but I'm not going to build my own hash, so, very interesting, Nathan. Well, the cool applications of this include, one, hashes are an O of 1 multi-tool. There's all kinds of algorithmic problems that you may be tasked to solve where the answer is use a hash. And the reason is because they perform so nicely. So if someone asks you how to dedupe a list, then a great way to do that is to go through and take each value and stick it in as a hash key, because next time you get a value like that, you'll be able to go and find out if it's in the hash very quickly. There's all kinds of issues that you'll run into with algorithms that can be solved by using hashes. They're a great, great multi-tool, and that's why we use them so often. Another thing is that all of these NoSQL databases everybody's talking about these days, some of them are what are called distributed hash tables. And the same principles apply. So DynamoDBs like React and Cassandra are distributed hash tables. So the same kind of thing applies. If you want to know what bucket do I find this in, aka what server is this key located on, they do the same sort of thing. They take your key, they hash it, they say, well, that would be on server number 7, and they go off and talk to server number 7. And the same penalties apply as well. So if you realize we've got more data than we can store on our existing servers, and we need to add some servers, well, when you add something, it has to rehash every key in your system, and it's going to take a while. So you might want to think, do I want to add one server and pay the entire rehashing penalty, or do I want to add 20 servers and pay the exact same rehashing penalty? Maybe we should add a bunch. So understanding how these things work does have real-world application for you. Well, I was thinking about all this stuff, but when I got another phone call, President Obama called me up. He said, dude, I thought you were going to send me that hash. I said, what are you talking about? I sent you an email an hour ago. He said, no, I've been trying to call you. Look, I got 10 missed calls. I look at my Outbox. It's stuck in drafts. I said, I'm sorry, Mr. President. I'll send it right away. He said, it's too late. Alien terrorists blew up SeaWorld. It was all a dream. Thank you very much.